Well, today we have a lesson that will cover the three issues you see on the screen. The first is we'll deal with questions that are about the division of polynomials. Okay. SAT questions that include polynomials are focused always on the division operation and the fact that when you try to do a division, you may have not always just an exact quotient, but you may have a remainder. Okay, so we'll deal with that. And one interesting tool that is called the remainder theorem. Then we'll see the notion of complex numbers. I know that you are acquainted with this, where complex numbers come from, the concept of imaginary number. So we'll see the basic notion of the imaginary unit, which is called I, and some questions related to this concept. And finally, we'll see how the absolute value can be interpreted when applied to functions. Okay, I've seen this concept in previous lessons, so it's not new, but we'll see a specific question type regarding absolute value and some tips that we can use to make these questions like straightforward, right? When we want to solve them. Well then, let's begin. First of all, in these days, you can actually have access to the information about evaluations in the GSG class platform. Just to know, for example, what is the result of the quizzes, how many questions you got right, etc. Okay. I try to make a comment, give you the input in the documents where each of you write the answers to the quiz of the corresponding class. You can see which answers you got right and which you didn't. Okay. As I said, it's just a reference because, you know, it's simply one set of questions that include all types of questions. Perhaps some questions that we are not completely familiar with yet because we haven't covered the corresponding theory. But I know that most of you, because you're about, either you already finish high school or are on the way to finish, have already seen many of the concepts involved. For example, now it's a fact that you guys in these days, you don't wait until the last year of high school to see trigonometry. I know that now trigonometry is seen even from the first year in high school. It's not like, you know, 10 or 15 years ago, like in my times, for example. You only learned trigonometry when you were in the last year of high school, in your senior year. But now it's not like that. You see trigonometry every year. So that's my point. Some of the concepts you may know already by heart because you have a curricula that allows you to have access to many of the concepts. The most important thing is how to use that information, that theory, to make it right through SAT questions. Okay, so let's talk about polynomial. We don't want to mess with the polynomials theory because that's not really the purpose. We want to get straightforward solutions and responses to SAT questions because, again, over and over, I will say this. What matters most in the SAT is speed, how fast you can get to the correct answer choice. Okay, obviously, this answer choice has to be the correct one, but you know, to be accurate here matters, but which matters most is how fast you get to the right answer. So remember this concept. when you talk about, for example, the division of real numbers, we know that when we divide real numbers, or think more in terms of the division of integers. It is good to illustrate this point. When you divide an integer that we call the dividend, and we divide it by some other integer that we call the divisor. Yeah, when this happens, the dividend divided by the divisor yields another integer we call the quotient. Okay, it's good. We talk about an exact division, right? We say that number D is divisible by small d, or that capital D is a multiple of a small d, etc. That's only in the case of the exact division. But what happens when there is no integer for the quotient? For example, when you divide, say D equals 45 and small d is 7. You do this division, you don't have an exact integer value. Of course, it may happen that you can get an exact real number or decimal number. Yeah, that's true. But an exact integer, no. So what happens? You do the division the way you're used to. Say the closest quotient would be 6. So this yields 42. You subtract this product from the original dividend, and the difference is what we call the remainder. So see, what is the relationship among these four numbers? Here, the dividend, the divisor, and this one is what we call the quotient, and this the remainder. There is this formula that connects the four terms of an inexact division. It says the dividend equals the divisor multiplied by the quotient plus the remainder. If you understand each of the terms and its place in the formula and why that place corresponds to each of them, then it's easy to understand the concept of the polynomial division. Say, for example, that you have a polynomial of degree n. Remember when we mentioned this, it's basically something like this, right? Let's say it's, for example, polynomial p, it's something like okay, a times x up to n plus b times x up to n minus 1 plus so on. You are decreasing the exponent of the terms up to having, for example, z times x plus a constant value k. Okay, that's a polynomial of degree n. Okay, indicated by this super index. Now, if you divide a polynomial like this by another polynomial, let's talk about a binomial of this form, a times x plus b. If you divide a polynomial by a binomial, you may obtain as the quotient of that division another polynomial whose degree has to be n minus 1. So if, for example, you have something like x cubed plus 4x squared minus 5x plus 1, and you divide this by another polynomial, a binomial actually such as x minus 1, what you get as the likely quotient is something like, for example, x squared. Yeah, it has to be 1 degree less than the original divisor. Okay, this is it. And this will be the quotient. And here you have this term, which is the quotient of the remainder divided by the original divisor. Pretty much like in this, if in this formula, I divide every term on the left and the right by the divisor, I have this. In an inexact division, the dividend over the divisor equals the quotient plus the remainder over the divisor. Okay? This figure here is the same as this. The remainder of the polynomial division, usually a constant value, divided by the original divisor. Either you can express the relationship like this, or in this linear form that we say, okay, the dividend in a polynomial division equals the divisor, which is usually, as I said, a binomial of degree 1, where the variable x only has exponent 1, multiplied by the quotient, which has to be degree n minus 1, and this product plus the remainder. So algorithms or procedures to find the division term by term, it's very similar to the division of integers, for example. It's very similar. There are some rules, right? Like you probably learn Ruffini, many methods. Okay, you are welcome to use whatever method works for you faster. But there is something interesting here. There is something interesting. There is some theory connected with this that is called the remainder theorem. What is the remainder theorem? The remainder theorem is an observation about the fact that when you do a division like this, okay, you can identify quickly what is the value of this constant r here, which is usually the remainder, right? Simply by evaluating the original dividend polynomial, that is p of x. You evaluate this polynomial in the value of x that corresponds to the numerical value that makes the divisor equal to 0. So what value makes this divisor a times x plus b equal to 0? Well, if you isolate x, the value would be negative b over a. So if you evaluate the original polynomial p in that very value, the resulting output will be the remainder of the polynomial division. So in other words, either you perform the complete division in order to find what is the quotient and what is the remainder, or you simply apply the remainder theorem if what they ask you is just to find the remainder. So we'll see several examples following. Let's see our first. Take a look at this. It says the expression 6 times x minus 5 divided by x plus 2 is equivalent to which of the following? So we need to find which one matches this expression. But that expression is a division, right? So method number 1. Let's say here that we do the division of polynomials. Remember, this is, if you are sharp about your skill to do polynomial division, no problem. Be my guest, you can do this fast. But here is interesting. You do the division, say, okay, 6x divided by x, quotient 6. Then multiply 6 by this and subtract from this. So 6 times x, I place it with the opposite sign. 6 times 12, negative 12, because I'm subtracting. Okay, once I do the subtraction, I cancel these terms, and what I get here is negative 17. So here it is all the information I need. This was the dividend. This is the divisor. This is the remainder. And what is this? Sorry, this is the quotient. And this is the remainder of the division. In other words, I can say that this expression 6x minus 5 divided by x plus 2, according to this structure here would be the quotient plus the remainder divided by the divisor. So what is the quotient? 6 plus the remainder, negative 17, divided by x plus 2. Which one matches? Option A. Okay, that's it. Now, what about another possibility? Say you don't want to mess with the division algorithm. What about doing this? Take a look. What about matching the expression above to something interesting is that in all the answer choices, you may see that 6 is like a term, okay, in the expressions. So what if I try to isolate 6 in this way? For me to be able to factor 6 as part, you know, of product of 6 times some binomial, here, since we have this in the denominator, I may say, okay, if I have x plus 2 here, what would I need to subtract? Because I have just made this term come out of the blue. 6 times 2 is 12. I am adding 12. I need to subtract 12. So I'm not actually modifying the original expression. 6 times 12 minus 12, that's 0, right? So you just keep 6x minus 5 divided by x plus 2. Then you can separate this and also this. 2 terms. So this is 6 times x plus 2 divided by x plus 2 minus 17 divided by x plus 2. Here it goes away and you get the correct expression, obviously. Okay, so 2 ways. Let's see another example. Here, you have when 3x squared plus 4 is divided by x minus 1. The result is a plus 7 over x minus 1. What is a in terms of x? Okay, here I'll make a pause and you may try to figure this out. Okay? Let's give you the chance to solve this one. You know, again, here there are 2 ways to do this. Either you do the division of polynomials, or you can do, you know, a rearrangement of the terms in order to find a match for A. Imagine this. Imagine you don't remember the division of polynomials, okay? Let's say you're not very clear about it. How can I still solve this? Take a look. You may say 3x squared plus 4 divided by x minus 1 has to be equal to this. Since they ask me to find A in terms of x, why don't I create a match? Try to force a match of the terms on both sides. First step, if I want to create a match of both expressions, why don't I try to put everything on the right side of the equality as a fraction? Because in the end, what is on the left side, the original expression is a division, is a fraction. So let's give common denominator. And this is it. I have now 2 fractions on both sides of this equality. So if the denominators are the same, it follows that the numerators must be the same. 3x squared plus 4 must equal a times x minus 1 plus 7. So what is a? Well, isolate a, you know. You have 3x squared plus 4, take away 7, equals a times x minus 1. This is 3x squared, take away 3. And finally, dividing everything by x minus 1, you have this. Factor 3, here x minus 1. And what can you see? Well, if you have done your homework about memorizing algebraic identities, the basic ones we saw in a previous lesson, right? For example, the difference of squares. Then you know that this part here can be factored, can be understood as 3x minus 1 times x plus 1. And so this goes away with this. Finally, you got A, 3 times x plus 1 or 3x plus 3. And that's it, option C. All right, that's one way. It's a little kind of long, you know. Much better is to do or follow the algorithm of the division, right? You may say this, I divide, let's do it from here, 3x squared plus 4 by x minus 1. Okay, divide this term by this. What you have is 3x. Multiply 3x by x minus 1 and subtract from 3x squared plus 4. So this would be 3x squared minus 3, right? So I place 3x squared negative. Instead of minus 3x, I place minus 3x. Remember, we are subtracting the results of multiplying this by this. So what happens when I do the algebraic sum? This cancels, but then I have 3x positive this time plus 4. So I continue the next step of the division. 3x divided by x is simply 3. So here appears the 3. Multiply 3 times x minus 1 and subtract it from this part. So 3x, negative 3x, 3 times negative 1, negative 3, but I'm subtracting, so plus 3. And what happens? It happens this. This goes away, 4 plus 3, 7, end of the division. This is the remainder. And this, all of this, is the quotient. So what is 3x squared plus 4? Is the quotient 3x plus 3 plus the remainder divided by the divisor. So this is it. Okay. So let's now move on to another related question, but this time we'll be able to do it much, much faster. Take a look at this. It says if the expression 5x squared minus 4x plus 1 divided by x minus 2 is written in the form 5x plus 6 plus b over x minus 2, where b is a constant, what is the value of b? Notice that if you pay attention to the form of this expression, you have here a polynomial of degree 2, here a binomial of degree 1, and this yields this expression, which is one polynomial plus a constant over the original divisor. This format only corresponds to what we saw originally, okay? To this here. So if we see a constant divided by the original divisor, it means that everything prior to it is actually the quotient of the division. So what do we have here is actually the divisor of this, the quotient of the division. And here, this one is the remainder of such division divided by the divisor. So they're asking me to find the remainder. How can I find the remainder? Obviously, one long way to do it is to do the division itself. Same way we've done the previous ones. But can I actually get to find the value of b without having to do the division? Yes, we can. How is that possible? If we apply the remainder theorem. What does the remainder theorem say? That if it is clear that in a division of a polynomial by a binomial of this form, you get a remainder, which is a constant value, then that remainder is exactly the result of evaluating the polynomial px, which is this expression, the dividend, evaluating here with a value of x that makes the divisor 0. So what value of x makes this part 0? Can you tell? Which x makes that 0? Not so hard, right? Yes. Then you know that if you evaluate the polynomial on value 2, constant value 2, what you get as a result, that is p of 2, is actually the remainder of this division. In other words, the value of p. So this is much faster. You can say simply, okay, p of 2 would be 5 times 2 squared minus 4 times 2 plus 1. Okay, this is 4, this is 20. Here we have 8 plus 1. What do we have? Okay, 12 plus 1 equals 13. This is it. Is that really so? Let's verify. Take a look. We are doing the whole division, okay? So that you can verify how this works in all cases. 5x squared minus 4x plus 1 divided by x minus 2. Notice that by doing the division, we will be able to identify what is the quotient, which is this part, and what is actually the value of b, the remainder. Take a look. 5x squared divided by x. Easy, right? 5x. Now multiply 5x by x minus 2 and subtract it from the original polynomial. So let's do that. 5x times x, here subtracting negative 5x squared. 5x times negative 2, that is negative 10x, but we are subtracting, so change the sign, 10x. And that's it. Let's do the subtraction. Here you have 6x plus 1. We just drop this other term. Okay, 6x plus 1 divided by x minus 2. Again, pick the first term and divide it by this. 6x divided by x equals 6. And multiply this 6 by x minus 2 and subtract it from this part. So 6 times x, negative 6x, since we're subtracting. 6 times negative 2, negative 12, plus 12, because we are subtracting. And so we have 1 plus 12, 13. You see? The remainder. And here, of course, we have the quotient. Exactly as in the original or the above expression. So these are the two ways, but here the remainder theorem provides us with a shortcut, okay, to solve this type of question. Remember, whenever they give you a polynomials division where they suggest this form and they ask you to find this constant value, which is divided by the original divisor, which acts as a sort of Q, right? Q to the quotient. Okay, then you can use the remainder theorem. Let's go back to the beginning to see what we discussed. What does the remainder theorem say? When you divide a polynomial p of x by a binomial of the form of first degree, a binomial of first degree, a times x plus b, where a and b are constant values, then to find the remainder of that division, simply evaluate the polynomial p in the value of x that makes the divisor equal to 0. So here you can see if we equal or equate this to 0 and isolate x, we get this value. So if we use that value in the polynomial, the resulting output is the remainder directly. Okay, so that's how you can try to do question number 4. All right, good answer, Luciana. Let's see, guys. Here, dividing this polynomial by the binomial x minus 3 yields some quotient plus the remainder divided by the divisor. So since it is the remainder we are trying to find, we can directly use the remainder theorem. Say, what is the value of x that makes the denominator 0? Actually, the divisor in the division, right? X minus 3. Well, that value is 3. So when x minus 3 equals 0, x must be 3. So if you evaluate the polynomial in the dividend using the value of 3, what do you get? You get 2 times 3 squared minus 5 times 3 plus 1. This is 9 times 2. This is 18. Take away 15 plus 1. So 3 plus 1, this is 4. This is the value of the remainder. So the answer to the question. Obviously, you can also do it following the longer procedure, which here has actually no practical value, right? It's much better to use the remainder theorem in order to solve the value of the remainder. If they ask you to find the value or to find the expression for the quotient, well, that's different. You have to divide. But if they ask you to find the remainder, apply the remainder theorem always, okay? It's shorter. Okay, so let's try now, let's move on to a different topic. Oh, one last example here. Actually, we have 2 more examples. They give you a polynomial, f of x, says, and in this polynomial, notice that the second term, the quadratic term, has an unknown coefficient, k, which is a constant, say. If this polynomial is divisible by the binomial x minus 2, what is the value of k? Can you use the remainder theorem to solve this one? I believe you can. You know, people, perhaps you may be doubtful about how to apply the remainder theorem here, since if they tell you that a certain expression or number is divisible by another, that usually means that there is no remainder. Yeah, if I tell you that 25 is divisible by 5, does a remainder exist in that division? No. The remainder, what is the remainder when a number is divisible by another? When we say that there is no remainder, what does your logic tell you? Shouldn't the remainder be 0? Right? So think about it. No remainder. Yes, no remainder means a remainder of 0. So if you use the remainder theorem in this way, you may say that since f of x is divisible by x minus 2, and this yields another polynomial g of x plus 0 over x minus 2. So what should be true if we apply the remainder theorem? It should be true that if we substitute the value of x in the polynomial here, in polynomial f, if we substitute the value that makes this divisor 0, the value of x would be 2. So f of 2 should be 0, the value of the remainder. And so we can simply say this is 3 times 8 to cube is 8 minus k times 2 square, which is 4, plus 5 times 2 plus 2. So what do we have? We have 4k equals 24 plus 12. So 36, and thus k should be 9. The answer to the question. Okay, so that's basically it. Okay. Remember, when a polynomial is divisible by a binomial of this form, then if you evaluate the polynomial in that very value, in other words, if they tell you that p of x is divisible by ax plus b, if you obtain this when you do the division, then if you evaluate p in the value negative b over a, the value that makes this 0, the divisor, then the output of this polynomial should be 0, according to the remainder theorem. Okay? Let's see if you can use the concept to solve the next question. Okay, so how do we do this? They tell me that there are the values for a polynomial p of x for several values of x, so we don't have a clue of what a polynomial is. And they tell me to find one factor of such polynomial. Well, what does the remainder theorem say? If this polynomial p of x is divisible by some factor of the form ax plus b, then if there is an exact quotient for this division, then if I evaluate p in the value that makes this divisor 0, in other words, minus b over a, then this output value for this polynomial should be 0, because there is no remainder when a polynomial is divisible by a certain factor. So what do we need to look for in the table given? Look for the value of p and the corresponding value of x, you know, that creates or satisfies this condition. What is the entry where the value of p is 0? Here. This corresponds to a value of x of -1, right? So this is interesting. It means that if you substitute this value in the expression like this, that actually makes the denominator or the divisor equal to 0. So think about this. The answer choices suggest that all the terms are of the form, the potential divisors we are about to evaluate are of the form x plus a constant value. No a, right? Yes, no a. So let's say that we have x plus k. If x plus k is made 0, when I substitute -1 as the value of x, then we have -1 plus k equals 0. And thus, the value of k is +1. So, this is the term. According to this, the correct answer would be x plus 1. Okay, be careful not to rush, since you identify that the value of x that makes that potential factor or divisor of p 0, -1, don't rush to say that x minus 1 is the factor. No, no, no. The factor should be made 0 when you substitute this value here in such factor. Okay? Fabiana, what's your question?
I didn't understand very well. Can you explain again, please?
Of course. What we said is according to an understanding of the remainder theorem, when you have a polynomial that is divisible by a binomial, in the division by a binomial of that form, that means that there is no remainder. Okay, that's divisibility. Divisibility is that the division is exact. So there is just a quotient, no remainder. The remainder theorem says that if you evaluate the polynomial dividend, that is p of x, by the value that makes the divisor 0, the value of x that makes the divisor 0, then you should obtain a 0 as the output. Only when that polynomial is divisible by the binomial we see here. So if they give you this table with several output values for this polynomial for given values of the variable x, we notice that when x equals -1, it exactly happens this, negative p of -1 equals 0. So what does that mean according to the remainder theorem? That because this output value is 0, that means that this x represents the value that makes the divisor in the division mentioned, that is this such factor of px, -1 makes that factor of px equal to 0. If we are thinking about a factor of the form ax plus b, okay, that could be good to say ax plus b equals 0 when x is -1. So a times -1 plus b equals 0. So what I got from here is that a equals b. Yeah, but that doesn't help me that much, right? Because a and b could be anything. But the point is this. I have 4 answer choices, and one of them must be correct. And in all the answer choices, the supposed value for a, this constant, is always 1. There is no alternative in the answer choices that has a value of a different from 1. So I assume that the factor is simply of the form x plus b. P of x divided by x plus b equals another polynomial of inferior degree q of x. Because of the remainder theorem, the value that makes this divisor 0 is exactly -1, because when I evaluate the polynomial in -1, I also get the output of 0. So x plus b is 0 when x equals -1. So I substitute this x by -1, and that yields me the value of b. B should be 1. So this expression is simply x plus 1.
Oh, okay. I got it. Thank you.
You got it? Very good. Let's now, people, move on. Okay, close the topic here and talk about complex numbers. Okay. Remember that the other day we were talking about quadratic equations, quadratic curves, and we saw this, that in order to evaluate quickly how many roots or solutions this equation has, we had to find the discriminant first, which is actually, right? The discriminant is this expression, oh, b squared minus 4 times a times c. Because in the formula, in the general formula, we have that the two solutions come from this. We said when the discriminant, that is this value here, the radicand in this expression, when that radicand is positive, that means there will be two solutions. When that radicand equals 0, that means there is only one solution, or if you want, the two solutions are the same. But what happens when b squared minus 4a times c is negative? Well, it doesn't exist a square root of a negative number. Well, everything is relative in life, they say. When we say it doesn't exist the square root of a negative number if we are talking about real numbers. But some very imaginative person decided to say, what if I invent the square root of negative numbers? You know, turned out that many years later, they discovered that the square root of negative numbers were actually a very powerful tool. And most of the progress that technology and science has seen in the last 100 years is simply because of the invention of imaginary numbers. Well, that's not actually a topic you will deal with in the SAT. But then, how did they define complex numbers? They happen to say, it's true that in the end, any square root of a negative number, say for example, negative square root of -5, is something that we can represent using the properties of radicals like this, the square root of -1 times 5. So it simply say the square root of -1 multiplied by the square root of 5, which actually exists, right? But what about this? Assuming any square root of any negative number takes you to this fundamental value. Does this exist as a real number? We know it doesn't exist. So somebody said, let's say that this is the imaginary numbers unit. They define this number, this imaginary number, and gave it the name of I. So I represents this imaginary square root of -1, which has an interesting property. What happens when you square a square root? Remember that what we said about it? If you square a square root, what happens? You obtain, of course, the radicand, x. So if you square I, or if you square this imaginary square root of -1, what you would get is -1 exactly. And you can continue finding powers of this basic imaginary unit I in the following way. If I want to calculate what is the cube of I, well, the cube of I can be understood as I squared multiplied by I again. But since I squared is -1, so this is the same as saying -1 times I, or simply I again. So negative I. right? This would be IQ. Now, what about I up to 4? Since I up to 4 is the same as, for example, I squared, squared again, and since I squared is simply -1, if I square -1, this will give me +1. And then it comes a cycle that repeats over and over. I up to 5 is simply I up to 4 times I. But since I up to 4 is simply 1, so it turns out that I up to 5 is again I. And the cycle repeats. I up to 6, -1, I up to 7, -I, etc. Well, using this property that the imaginary unit I has, we can define operations, right? When a number is thought to have a real part and an imaginary part, then we talk about complex numbers. And usually the notation is like this: A plus B times I. We represent these numbers as, you know, points on a coordinate plane. Imagine this coordinate plane where the horizontal axis is the real domain and the vertical axis is the imaginary domain. So by saying A plus B times I, we mean some horizontal position over the real number line, A, and a vertical position over the imaginary number line. So here, B. Here, the unit, of course, on the real line is 1. The unit on the imaginary number line is I. Okay, let's say here is I, here 2I, etc. While here is 1, 2, etc. So what is this A plus B times I? Is simply this. This point on this plane is the representation of complex number A plus BI, where both A and B are real numbers, but this is the imaginary part and this is the real part of the complex number. Okay, so we represent complex numbers as points on a plane as if they were, you know, two coordinates, right? To represent points. But turns out that this is a very useful construct, you know, in many fields of math applications, even in physics and engineering. Well, complex numbers work like this. You can do some basic operations. For example, whenever you see a question like this, if I equals, okay, the imaginary unit, the square root of -1, which of the following is equivalent to 3 plus 5i minus 2 minus 3i? Remember, when you see expressions like this and they ask you to add or subtract real numbers, treat the I as if it were some kind of X. How would you solve this? How would you solve 3 plus 5x minus 2 minus 3x? Wouldn't you reduce like terms, constants with constants, and variables with variables, right? You wouldn't mix the two. First, you would open the parentheses here, minus 2 plus 3x, and then you operate this and operate this versus this. And that's it, no problem. 3 minus 2, 1. 5x plus 3x plus 8x. And that's it. Do the same when you have to operate imaginary or complex numbers. Those expressions with the I operate, add them, or subtract them together. Those constant values, the real part of these numbers, operate them together as well. Okay, so what would be the equivalent here? According to what we've already done, of course, since I use exactly the same coefficients, this would correspond to this, right? It would be option C. It's simply doing this. 3 plus 5 times I minus 2 plus 3 times I. So 3 minus 2, 1. 5I plus 3I, 8I. And that's it. Let's see another example. What would happen if they asked you to multiply? So what would you do if you had to multiply this, for example? 3 plus 2x times 5 minus 7x. It's easy, right? You apply the distributive property. Multiply this times this, this times this, this times this times this, and then reduce like terms as much as you can. Well, why don't you follow the same approach when you try to multiply complex numbers? Say, for example, you have to multiply this times this. Saying exactly the same approach. But remember, if you get to multiply I times I, remember what happens when you have I squared. That can be substituted by simply -1, because that's how it is defined. Okay, so let's see the next question. Here. Okay, very good response, Luciana. How do we do this? Take a look. Multiply 4 times 5. Okay, let's rewrite this. 4 times 5, 20. 4 times -2i, -8i. I plus times 5, that is 5i. I times -2i, it would be -2i squared. So you reduce this, it's -3i. But what happens with 20 and -2i squared? We don't see any of these options in the answer choices. Well, it's simply that. Take a look. What is I squared, did we say just a moment ago? The square of I is -1. So you have this 20 minus 3a minus 2 times -1. So these two negative signs cancel and you get 20 minus 3i plus 2. So 22 minus 3i. Okay? Yes, that's it. Okay, let's see one more example. It says, which of the following is equal to plus 3i over 1 plus I? Well. What would you do if you wanted, for example, to solve this question? Let me just give you a hint. 2 plus 3 times the square root of 5 divided 1 by 1 plus the square root of 5. What would you do in order to rationalize this expression? To transform this expression in such a way that you don't see the square root of 5 in the denominator, only in the numerator possibly, what would you have to do? Remember what you did to rationalize this? What we did is this, right? Multiply above and below by the conjugate of this. So 1 minus square root of 5. Here the same, not to change the value of the whole expression. What is the effect of doing this multiplication in the denominator? The sum times the difference of two numbers is the difference of squares. Yes, so the denominator would be the square of 1, take away the square of the square root of 5. Here above, of course, you would multiply this by this, but here, the effect of squaring this square root will eliminate the radical. So this will be 1 minus 5. Good. Can you do perhaps something similar in order to remove this from the denominator to obtain actually a complex number? Remember that I, in the end, is simply another square root, the square root of -1. So what would happen if you try a similar approach? Would you be able to get rid of I in the denominator? Yes, you would. So try this one. Okay, let's see. So what can we try? We said multiply both numerator and denominator by the conjugate of the denominator. If we do this, then of course, this product, we can apply the same identity we used here. If you multiply the sum and the difference of two numbers, you will get the difference of squares. So what is this? In the denominator, we have 1 minus the square of I. In the numerator, we have 2 times 1, 2, 2 times negative I minus 2I, and you have 3I times 1 and 3I times negative I, that is negative 3I squared. Okay, what happens in the numerator? These two are simply I, and you have 2. And here, because I squared is always -1, -1 multiplied by -3, that's +3. So you have this. Sorry. And in the denominator, you have 1 minus -1, which is the square of I, right? So simplifying, I plus 5 divided by 1 plus 1, 2. Okay, separate this into portions. The real portion, the real part, 5/2 plus 1/2 times I. So you have there the complex expression. Option D. Okay, that's how you do these divisions.
Could you explain it again?
Okay, which part didn't you understand, please?
I can understand like why I get it like the process, but I don't get like when you multiply it by 1 minus I. Like I understand the rest, but I don't get why you like multiply it.
Do you understand why here I multiply this by this? Why did I do it? Did you listen to what I said?
I listened, but I didn't get it.
Okay, you listened, but you didn't get it. Can
It's
anyone try to comment on what your classmate is saying? Anyone of you 3 people understand why we multiply this by this? Okay, you understand the result. If you understand the result, then you must be able to tell the why. What's the reason? Why did I do that? Why did I multiply the sum by the difference? Difference of squares. Thank you, Axel. Thank you. And what's the purpose of doing the difference of squares?
To get rid of the square root.
Eliminate the square root. Perfect.
Well, I get it. Yeah,
eliminate the square root. When we multiply 1 plus I times 1 minus I, we are eliminating the square root that I means. Because the moment we get I squared, we can substitute I squared by a real number. That is one advantage of working with I squared. I squared is a real number. it's like confusing, because how come an imaginary number may become a real number? Well, but that's the definition, right? Let's go back to the definition. If we are defining I as the square root of -1, an imaginary square root, but that means that if we square this number, you get the real number -1. That's exactly the purpose of defining I. Okay, so here, when we multiply these two, we are making I square appear. And since I square is a real number, then we get rid of the I in the denominator. Why? Because we can only define a complex number when we have the format A plus B times I. In this format, you see a sum of two terms, one of which possesses I, but not I in the denominator. So when I is in the denominator, we need to remove it from that position. And we remove it by using the difference of squares. Okay, let's move on now to the next topic of today. This is the hardest you will see about complex numbers in the SAT. Well, that's good news, because they don't really ask you, for example, to apply transformations or rotations of complex numbers, which is actually much more complex. You won't see questions like that. This is all you will see about complex numbers in the SAT. Okay, so let's move on to the next topic, absolute value. Now, we've talked about absolute value. How should we interpret absolute value? Remember, we said something in a previous lesson. The absolute value of x is the distance between x and 0, okay? That's the first concept. Since distances are always positive, the distance between x and 0, that's the absolute value of x. Because no matter to which side of 0 x is located, the distance from this number to 0 will always be positive. So that's why when the number itself is positive, its distance to 0 is simply the same number. But if the number is negative, its distance to 0 is simply the result of multiplying that negative number, by -1. So negative x gives you the distance or the absolute value. It's a way to say that whenever you place the two vertical bars of the absolute value on the sides of an expression, you are positivizing that expression. If the expression is positive, it remains positive. If the expression is negative, it turns positive. That's it. But there is another interesting trick. How to interpret this? The absolute value of x minus k, where k is a constant value, positive or negative, no problem. But x minus k in absolute value always means this is the distance between x and k. Don't forget that, because that is a useful construct to manipulate expressions like this. So say, for example, how do we understand this if they tell me that the distance, that a number, for example, right, must be at a distance of 2 of some constant -7. So if the distance between a number x and -7 must be 2 units, I can express this by saying x minus -7 in absolute value must be 2 units. This means that the distance between x and -7 is 2 units. Of course, here the double negative turns x plus 7 equals 2. But what does this equation originally means? That the distance between x and -7 is 2 units. You can see this on a number line. Here is 0, here is -7, and a number that is located 2 units away of -7 could be either -9 or could be either -5, right? because both numbers are at 2 units away from -7. And these exactly are the values of the solution of this, right? So that's how you can see that this notation, comes handy to manipulate certain expressions with absolute value. Now, another interesting thing, how do you interpret this? The absolute value of x minus k is less than a positive units. What this means is the distance between x and k is less than a units. So imagine this. On a number line, you have this number k. And think about a positive units as trying to plot like a circle, like some sort of radar here, okay? A units in all directions. Obviously, a units here would be k plus a, and a units to the left would be k minus a. So where is x? X is in any of these possible positions, because any number in that shaded region of the number line will always be less than a units away from k. Okay, so how do you interpret this then? X minus 2 is less than 3. It means, again, if in a number line I place 2 as my pivot value, that is to say that if I move to the right, I move to the left or the right, no more than 3 units, I get to the end values of -1 and here +5. In other words, for this to be true, what it means is that x is simply a value between -1 and 5. And that's it, the solution. Yeah, is there an analytical way to do this? To get to this range of values from the original expression? Yes, here is the key. Whenever you see something like this, okay, you can open it directly like this. If x minus k is less than a units, it means that this here is between -a and +a. So add k in order to isolate x, and you get add k in all the 3 parts of this double inequality, and you have k minus a less than x less than k plus a. And that's it. The solution to this inequality with absolute value. On the contrary, if they ever tell you that, for example, the distance between x and a certain number k is greater than a units, it means something like this. Imagine, here is a number line, here is k, and since we consider here a range of a units all around k, here would be k plus a, here would be k minus a. X must be outside this region. So it could be here or it could be here. Any number in these shaded regions will be always more than a units away from k. So how do you see this? We can see that the opening of this inequality from the diagram, which translate this as distances between numbers on a number line, would be x could be here, that is to say, x could be less than k minus a, or x should be in this part, should be greater than k plus a. And that would be it. Or if you want, you could say x minus k is less than -a, or x minus k is greater than a. This is the way to open this one. This is less than the negative constant or greater than the positive constant. the two ways to open inequalities like this. With absolute value, of course. So let's see what kind of questions you're supposed to deal with. Functions with absolute value. How many integer values of x satisfy x in absolute value is less than 4? So now you can see how to open this. Can you try? Okay. Please do. Let's see the answer. It says absolute value of x less than 4. So how do we interpret this? Since here don't have, right, like some x minus k, so that k could be 0. It's simply the distance between x and 0 is less than 4 units. So you can directly, open this in these two parts. You can say x is actually less than 4 and greater than -4, and that's it. Or you can try to visualize this on a number line, saying the distance between x and 0, here is 0, is less than 4 units. So if it is less than 4 units, imagine here a radar covering 4 units in all directions from pivot value 0. And so here you get to -4 to the left and +4 on the right. Since the distance should be less than 4, it means that x must be here. So this exactly matches this, of course. Okay, how many integers exist in that range? Notice, be careful with the symbols less than and greater than. So that means that -4 and 4 are not included in the range. Here you can count -3, -2, 1, 0, 1, 2, and 3. So how many values exist? How many are here? Totally. Because all the values I've just written are integers, right? Yes. 0 is an integer, by the way, don't forget that. And there are positive and negative integers. So how many integers comply with the condition that the distance between x and 0 should be less than 4 units? Okay, all of them. 7 values. All right, that's the answer to the question. Any doubts about this? Is it clear when you see the diagram? We're counting all integers in that range, right? Between -4 and 4. Okay, 7 integers in between. Well, let's try the next. How many integer values of x satisfy the absolute value of x plus 1 is less than 5? Can we interpret this in terms of distance between x and a certain number and in terms of how many units could that distance be? Yes, we can. So you can try. Remember the pattern? Absolute value of x minus k is less than a constant value a means that the distance between x and k, here k is the pivot value. Be careful with this, right? Be careful with this sign here. Okay, so if you think about a distance of a from this pivot value k, it means it can extend in all directions. Actually, there is just 2 directions, left and right. Here, you should get to k minus a, and here k plus a. And so, since x must be at a distance less than a units, x must be here. Any of these possible values for x. Okay? So, using this approach, what would be the answer this time? Or you can directly, instead of going like this, you can directly go and open this like this. X minus k is greater than negative a and less than k. And from this double inequality, isolate the value of x, right? Sorry, here is a, not negative. Between negative a and a. And from this, of course, you can have x between a plus k and k minus a. Right, so first let's open this inequality the direct way. X plus 1 must be between negative 5 and positive 5. In this double inequality, I may subtract 1 on each of the three parts. So, like this. And I get how many integers exist in this range? Okay, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, and 3. Totally 9. So this is the answer to the question. Okay, good answer, Luciana. Let's try more example. Example number 3. Here you need to use a little bit of a logic, right? To understand this. Does it make sense in the first place that the absolute value of any expression could be a negative number? Can that be possible? What did we say about absolute values? They must be always positive, right? So how come the absolute value is less than 0? How can that be? That simply doesn't exist, right? If that doesn't exist, could there be a value of x that satisfies the inequality? Not at all. Here, the correct answer is this. It doesn't make sense either if we use the geometric approach that we just discussed about distances. Does it make sense to say that the distance between 2x and 5 is less than 0 units? Doesn't make sense. How could there be a distance less than 0? No. So that's the answer to the question. Let's try one more. All right, how do we approach this one? When you read this word problem, you can really understand that the possible values for the weight of the cookie package can be expressed with a double inequality, right? It says that the acceptable weight for the cookies package is between 16 and 18 ounces. We define the variable W as the weight of the acceptable cookie package. So what are they telling you? With this statement, they are telling you that W needs to be between 16 and 18. Which one of these inequalities corresponds to this one? What can you do? Okay, you can do here two possible things. If you were a little like unfamiliar with the concept of this expression, okay? If you were unfamiliar with this, you still don't understand this, you can try the direct algebraic approach and open each of the inequalities to see to which, which of them matches this. For example, let's try the first one. The first one says W minus 17 is greater than 1. So according to the equivalences we saw, this directly opens as W minus 17 is less than negative 1, or W minus 17 is greater than 1. But this will never give you an inequality like this, because this is the other way, right? They're telling you that W minus 17 is actually, here's negative 1, here is 1, two possible regions for W minus 17. So this will never be like a dual interval like this, or just a single interval, you know, which is bound on the two ends. So what about this one? If you ever want to get a correspondence with this, look for the inequality symbol less than. So from this approach, simply logic, let's just cross out this and this. Let's just try B and D. Okay, W minus 16 in absolute value is less than 2. It means that W minus 16 must be between negative 2 and 2. So add 16 in each of the parts, and you get 16 minus 2, 14. W and 18. Does this match? No, it doesn't. So obviously it must be this one. We have no more choices to try. Okay, so that's one way. But another way interesting is this. Imagine that if W is between 16 and 18, imagine that this on the number line, let's do this with another color, is something like this. There is this range, 16 and 18. And in the middle of it, is the pivot value that is at the same distance from this end and at the same distance from this end. What is such value, such numerical value, that is at the same distance from 16 and 18? Wouldn't that be actually the average, 17? And wouldn't this be just 1 unit and here 1 unit of distance? So what does this shaded region represent? According to the notation we saw, it means that the variable is less than 1 unit away from number 17. How do we represent this? Directly. W minus 17 in absolute value, that is the distance between W and 17, is less than 1 unit. So that's it. You can obtain the inequality reasoning from the concept of distance or bound distance on a number line between a variable and some pivot value. Okay, so that's it. Let's try one last example. Okay, before going to the next example, remember something. When you see the absolute value of a function, okay, remember that y, we say y is the same as f of x. For example, this linear equation or linear function x, it has positive values of x and negative values of x. Of course, x can take any possible values. Positive here, negative here. But what happens with y or f of x? In this linear function, y can take positive values here, but it can take negative values here. So, is that possible for the absolute value of some function? No. For example, if we take the absolute value of x, then since y is the absolute value of x, y can never be negative. Since it can never be negative, in the region where the values of y were supposed to be negative, that is on the, you know, left side of the x-axis, it needs to be like reflected. Imagine that you reflect this in this direction, because the values of y must always be positive. So if you make these negative values positive, it has this shape like a V shape. Okay, now imagine that we had any other function. Imagine that you have y that is f of x, okay, like this. Imagine you have this. Imagine you have a curve like this, perhaps. For example, what happens, as you can see here, there is one part of the values of y here are positive, but to the left, the values of y are negative. So how would the absolute value of x, of f of x, would look like? The absolute value of f of x would look like this. I will draw it, but using the same diagram. Instead of this portion, which is negative, you would have something like this. The blue line shows what the absolute value would look like, okay? This would be the absolute value of f of x, while the original function may have, of course, positive or negative values. So, thinking about this, which of the following could be the graph of y equals the absolute value of 2x minus 1? Let's see the answer to this. First, what kind of function do we have here? Is the absolute value of a linear function. Because if we say y equals to x minus 1, what is that? It's a straight line on the plane. So if we take the absolute value, it's like the negative portion of that straight line, that is the portion of the line that goes under the positive, under the horizontal axis, will have to be twisted up, right? Or like flipped up. Which one can reflect that? So the principle is, because this is an absolute value, y can never be negative. So it couldn't be this. This has a negative portion here. It couldn't be this. It has this negative portion, vertically speaking. So we have D or C. So which one is better? Think about it. If it is a number line or a straight line, 2x minus 1 looks like this. If you flip this part upwards, it will look like this. So it makes sense that it's C. What happens with D? Okay, D has like, several portions, and it has like 2 zeros. It's impossible that this expression will have, 2 zeros, right? Linear equations or linear functions only have 1 zero, not 2. So because of this, the correct answer choice is option C.